Hello everyone, welcome again. So in this segment, we are going to continue with multiple operations of binary search tree. So let's start. All right. So first we are going to see the data structure implementation of binary search tree. So a binary search tree is actually the data structure of binary search tree is same as binary tree. So you can see that the structure is same. So our class definition means the class definition for the binary search tree node is actually same as the binary tree node. Okay. But when we are going to implement the operations, we have to redefine the operations for binary search tree. Okay. All right. So let's look at the class definition for the binary tree node class. So a binary tree node means a binary tree node means it's a binary tree. So every node can have at most two children. So it can have a left children or right children. Okay. So how we are going to implement that? How we are going to write the class definition? So for binary search tree node, every node is going to have the data value. Okay, every node is going to have the data value, and every node can have a left children. Okay, if it doesn't have left children, then it will be null. All right, or it can have a right children. So if it doesn't have a right children, then the right children is going to be null. All right. So the in the class definition of binary search tree, we are going to have these following member variables. So it is going to have the data value. Okay, we are assuming that each node is going to store only the just one integer value, and it is going to have a pointer. All right, pointer that will point to the left children. All right, so and the left children can be also the root of another tree. Okay, so that's why it will be the same type of pointer. So bst node type of pointer left. So it is going to have another pointer that is going to point another bst node. All right, so these following member variables are going to be the member variables of the bst node. So then in the member function list, we are going to list all the constructor, accessor function, mutator function. Okay. All right. So that's the very simple class definition. And also we're going to list all the operations of the. All right. So, but when we're going to implement the binary search tree with the BST node, we're going to list all the operations of the binary search tree. Now, this is the class definition of the binary search tree node for each node. Okay. So let's look at the constructor definition. You can see that. So the first one is the default constructor. So this constructor means when we'll initialize a binary search tree node with this constructor, the default value can be 0 and both left children are and right children are null. Okay. So that is the definition of the default constructor. So the second constructor, we are initializing the BST node with a value, okay, with a specific value. So with a specific value, any value, let's say 10, okay, and the left children and right children both are null. Okay, so that's for the second constructor. And for the third constructor, we can initialize the BST node with both with value and also the pointer. Okay, pointer for left children and the right children. So let's say you have one subtree here like this. Okay, so using this constructor, you can actually initialize a BST node, all right, with a specific value. Let's see, the value is 10 and left children is, okay, a specific node, all right, and right children is another specific node. All right, so you can do that using this constructor. So XSR function means all the get function. So you can see that XSR function, and these are the all mutator function means all the set function. All right. Now we saw the class definition of binary search tree node for each node. Now, now this is the class definition of binary search tree. All right. So a binary search tree. So a binary search tree means a binary search tree is a collection of binary search tree node. Okay, means all the binary search tree node or yeah, binary search tree node or binary node. Okay, so now in the binary search tree we have to list also all the operations. Okay, now what a binary search tree means, when we are going to initialize a binary search tree, that will have only one node, which is a binary search tree node and which is the root node. Okay, and when we'll initialize the binary search tree, it is going to look like that, a binary search tree. And you can see that we are running the default constructor of the binary search tree, and the root will be just a root is going to be a null value. Okay, root is going to point to a null value. Okay, all right. Now in the binary search tree, we're going to list all the operations of the binary search tree, and we have to figure out, when we're going to implement a data structure, what operations should have a binary search tree. Okay, what operations you should list in the binary search tree. So this is a very basic operation, a binary search tree. We can find out whether the binary search tree is empty or not. So if a binary search tree doesn't have any value, that means it's an empty binary search tree. All right. So find a node. Find a node means given a value. All right. We want to search a node in the binary search tree. All right. So insertion of a node. So you have an existing binary search tree like that. Okay, now we want to insert a node. So obviously when we insert a node, we have to insert a node so that it doesn't violate the binary search tree properties. Means after the insertion also, the node has to be, the node should follow all the properties of the binary search tree. So deletion is also same, means we can only delete a node from the binary search tree. For example, like I want to delete this node. Okay, but when I will delete a node from a binary search tree, I have to make sure that after the operation, the tree has to be still the binary search tree, means it has to follow all the properties. Then few other operation, like I may want to find the minimum value, okay, the maximum minimum value or the maximum value, and also the traversal algorithm. Okay, all right, so let's see the first operation. Let's see, the first operation is that I want to find an element in the binary search tree. Okay, so as we said in our earlier discussion, that means why do we need to learn a new data structure? Okay, so there should have a there should be a motivation why we are learning a new data structure. So the binary tree give us a hierarchical structure. Okay, all right. Now we see that in a ordinary binary tree or in an ordinary list data structure, finding an item in a list data structure or a ordinary binary tree means we have to traverse all the nodes in that data structure. Okay, now that doesn't mean a efficient solution. If you have a lot of node or a lot of items in your data structure, that is going to, that is going to be a linear algorithm, but we have to look for always, can we make it better? All right, so in a binary search tree, the way we are ordering each of the items, we keep all the items that is less than the value x is in its left subtree, and all the items that is higher than or greater than x, we keep them in the right subtree. Okay, and this is the properties we are going to use to make our searching more efficient. All right, so let's see an example how we can find a item more efficiently in a binary search tree. Okay, then we're going to see the algorithm for finding an item. So let's see, we have a binary search tree. Let's say the root is 10, and here we have, let's see, 5, so 20, so 3, 6. All right, so 1. Okay, and let's see, here we have 4. All right, and let's add some node in right subtree. So let's see, here we have 15, 25. All right, so here we can have like okay, let's see, 22. Okay, and we can have here 35. All right, so that's a binary search tree. Okay, so you can see every node here are less than 10. Okay, and every node here are greater than 10. Okay, and consider every possible subtree here. Consider every possible subtree here, they are also following the binary search tree properties. Now in this following binary search tree, let's find out some node. Okay, let's find out some value. So let's say we're looking for a value x equals to uh, 3. Okay, so let's find a value 3. So the way we are going to approach here, okay, we're going to start from the root node. All right, so we're going to start from the root node, so 10. So the root has the value 10. Now we are going to see whether the item we are looking for, x, is greater than 10 or less than 10. Okay, now 3 is less than 10. Okay, so first we are going to look for whether the item we are looking for is same as the value of the root node. So the root has the value 10, so 3 is not equal to 10. Okay, so then we are going to check whether 3 is greater than 10 or 3 is, sorry, 3 is less than 10 or 3 is greater than 10. So looks like 3 is less than 10. So that means actually we can skip all the values that are in the right subtree of 10. Okay, because 3 is less than 10, that means it is going to be in the left subtree of 10. Okay, so what we can do, I can skip every node that is in the right subtree of this value 10. Okay, so what we are going to do, from 10 I'm going to go in the left of 10. All right, and I'm going to actually follow the same thing. Okay, follow the same rule. Now go check the left children of 10. Looks like this is 5. Okay, then I'm going to check whether 3 is same as 5 or not. Okay, so 3 is not same as 5. Okay, then I'm going to check 3 is less than 5 or 3 is greater than 5. Okay, so 3 is less than 5, not greater than 5. So what I can do now, I can skip all the values that is in the right subtree of 5. Okay, just skip all of them. I do not have to look at that, because I know that if the value exists in this tree, all right, that is going to be in the left subtree of 5. Okay, so then now move forward and traverse in the left direction. Okay, so go to the left children of 5. All right, now you can see that I have the value 3 here. Okay, so now let's looks like 3 is same as the value 3. Okay, means I found the value. Okay, so I can see that, I can say that I found the value. All right, now let's change the color. So what if I'm looking for the value 6? Okay, so I'll check the root 10. Okay, 6 is less than 10. All right, so where I have to go, I have to go to left of 10. I can skip everything in the right of 10. Okay, so now I found, now in this subtree root is 5, and I can see that 6 is greater than 5. I mean 6 is not same as the value, and 6 is greater than 5. So where I have to go? I have to go to the right. As 6 is greater than 5 means I can skip every items in the left subtree. I have to go in the right of the node. Okay, so I'll go to the right of 5, and here I can see I am finding the value 6. Okay, now same way let's find let's see, x is 22. Okay, so root is we're going to start from root is 10. 22 is greater than 10, so we'll go to the right. Skip everything from the left, go to right. So now the value is 20, and 22 is still 22 is greater than 20. So I have to go again right. So I can skip everything from the left of 20. So go to right, 25. So now 22 is less than 25. So where I should travel. Okay, so where should I go? I have to go to the left. Okay, here I find the value 22. Okay, now what is the worst case here? The worst case is that, let's see, I'm looking for an item which is not in the tree. Okay, let's find the item 13. Okay, 13 is not actually in the tree, so how that is going to work? So so start from the root 10. 13 is greater than 10, so it should go to the, it is going to go to the right. Okay, now the root is 20 in this right subtree, 20. Okay, so 13 is less than 20, so it will go to the left. Okay, go to the left. Now 15, so 13 is greater than, sorry, 13 is less than 15. Okay, so again go to the left of 15. Now left of 15 is null. What does that mean? So if we are looking for item and we are following the direction, right direction to find the item, but if we did not find the item, and if we reach the null value, okay, if we reach the null value, then we can say that, okay, the value doesn't exist in this tree. Okay, in this example 13 doesn't exist in this tree, so we can see that we are following the direction. Okay, we go to the right, then left. Now here we should go to the left because 13 is less than 15. We will go to the left. Okay, 15 has actually the left children is null and right children is also null. Okay, now we go to the left and we can see that now the value is null. If we reach to the null value, okay, then we can see that we can say that the value doesn't exist in the tree. So just another more example, let's find the value 45. Okay, we start from the root 10. 45 is greater than 10, go to right. 45 is greater than 20, go to right. 45 is greater than 25, go to right. 35, so 45 is greater than 25, so go to right. Now right has null, so you are here. Okay, now you can see that the value is null, so you can say that 45, the value that we are looking for, doesn't exist in this tree. Okay, so how do we implement this algorithm? So most of the operations in the binary tree and binary search tree we can actually implement using recursive approach. Okay, but also you can implement is using iterative approach. So the way I'm talking about it, actually you can see the way I'm actually showing you the solution. We can actually implement the same way, and using the iterative approach you can actually see what actually I'm doing. Okay, but also you can implement the same function using recursive approach. because the binary search tree or the binary tree is actually like a follows the recursive structure. Okay, because each of the left children, okay, can contain another subtree. All right, so let's look at the iterative solution first. Then I'm going to actually leave finding the recursive solution up to you. All right, I'll ask you to think about the recursive solution. Okay, I'll give you the idea and I'll ask you to find the recursive solution, and we're going to discuss more about that in the next class. So the iterative solution, we can see actually how to find a item in the binary search tree. So what we are doing here, we start from the root node. Okay, now depending on the value, we can have three options. All right, so the value can be same as the value of the root node, or the value can be less than the value, less than the root node, or the value can be greater than the root node. So depending on these three options, okay, so if this is same as the root node, means we find the item, but if this is less than the root node, we'll go to the left, but if this is greater than the root node, we are going to go to the right. Okay, and we are going to continue the same approach until we find the value or until we reach to a null pointer. Okay, if we find the value, then we find the value, we print that we find the value. But if we didn't find the value but we reach a null pointer, okay, that means the item doesn't exist in the tree. So let's look at this function definition, and you can see actually how we are implementing this. Okay, so this is the function we're going to write as a member function of the binary search tree. Okay, so inside a binary search tree, you want to find a value, and we are going to find a value using the parameter data. Okay, so the data is given, and we are going to find the value in this binary search tree. So initially, we are going to just have a boolean flag. Okay, so initially we are going to mark the flag as a false. Okay, all right, so first we are going to check whether the data is whether the tree is empty. Okay, that if the tree is empty, that means actually I mean there is no node in this binary search tree, means we are going to just print that the tree is empty. Okay, now what actually we're going to do, as we did in our list traversal, all right, list data structure traversal, we're going to have a temporary pointer. Okay, we're going to use another pointer that is going to traverse the whole tree. All right, now we know that we have a pointer, root pointer. So we have a pointer, root pointer, that will point to the root node. And for a binary search tree also, this is the pointer we have to have always, that should point to the root node always. Okay, means in no way we can actually move this root pointer. Okay, because this is the address actually that will give us the every information of this binary search tree. Okay, so what we are going to do, we are going to declare another pointer, current pointer, that is we are going to use to traverse the whole tree. All right, for example, declare another pointer, current. Okay, we are going to initialize current as a same as the root node. That means current will point to the same pointer that root is pointing. All right, so this line means current is pointing to the same address that the root pointer is pointing. Okay, so this will happen after this line. All right, now we are going to run a loop. So we're going to run a loop until we find a null value. So while the current is not 0, means actually this is same as writing while current is not null. Okay, so we're going to check that the data value of the current. Okay, so first we're going to check that the data value as the current is same as the value that we are looking for. Okay, so these are the data we are looking for, and we are going to check that this is the same as the data value of the current. So if this is same, all right, So that means we found our value. Okay, that means the data is found. So what we are going to do, we are going to make our flag true. Okay, so we are going to print that the data is found, okay, in the tree, and we are going to return from the function. And what we are returning, we are returning the address of the current. Okay, so the point we find the value means we can actually return from the function. We don't have to traverse anymore. We're going to print that the data has been found and return the address of the current. Okay, the current node. All right, now if this is not the same, we can have two other options. Okay, so the data can be less than the value, okay, this value, okay, x, or the data we are looking for can be greater than x. All right, so if the data is greater than x, this is the condition. If the data is greater than x, means data is greater than current of data. Okay, all right, so then we are going to move current to the right of the current. Okay, means we are saying go to the right of the where you are right now. Okay, now you are in the root. Okay, go to the right of the root. Okay, go to the right of the current node. All right, now else we are asking them to go to the left. So if data is less than x, go to the left. Okay, and the same string will be repeated until we find a until the current is pointing to a null value. Okay, so based on the value of the data, it can traverse in any left or right direction until the current is pointing to a null value. Okay, so whenever it finds a value, okay, you can see that here actually we are returning this because like whenever it is going to find a value, it doesn't have to traverse the tree. Okay, it doesn't have to traverse the tree anymore. It is going to return from the function. All right, now what happens when it reaches to the null value but we didn't find the value? Okay, means now it will be at this point. So if your program is at this point, means actually found is still false. Okay, we haven't updated the found value because we could not find the value. Okay, so found is still false. Okay, and we are here because we have actually completed the whole iteration from our while loop. Okay, so and found is still false, and we can say that data not found. All right, so this is the same thing actually we just described here, how we can find a value from the binary search tree. All right, so you can see that the clear difference between finding an item from a binary search tree versus binary tree. So in the binary search tree, in each iteration, okay, we are actually what we are doing, we are reducing our problem size. Okay, in each iteration, we can skip the whole subtree, either the left subtree or the right subtree. Okay, we are going to only look for in only one subtree. Okay, that is reducing our search space almost in half. Okay, so for example, you can see that our worst case can be actually when the item is not there. Okay, when the item is not there, and in this example, when the value is 13, we are looking for, this is our worst case because the item is not there, um, means actually we have to traverse until the leaf node. Okay, until we find until the current is pointing to a null pointer. Okay, but even in the worst case, what is actually the number of comparison? Okay, so for number node 13, the number of comparison was 1, 2, 3. Okay, 1, yes, 1, 2, 3, and here we are going to stop. All right, so the number of comparison was actually, you can see that 1, 2, 3, 4. All right, and here For this also another example of worst case, because this doesn't exist in this tree, you can see that the number of comparison was 1, 2, 3, 4, and 5. Okay, and how many node is in this binary search tree? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, all right. So here um, what happens here? Okay, if we want to find the runtime of the operation, all right. So if we want to find the runtime of the operation, you can see that what is going to be the runtime of the operation. All right, does that depend on the number of node in the tree? It doesn't actually depend on the number of node in the tree. It depends on the height of the binary tree. Okay, it depends on the height of the binary tree. Okay, all right. So all right. So that makes the searching operation more efficient in the binary search tree versus in the binary tree. Okay, in the binary tree or in the ordinary list. Okay, we'll talk more about the runtime operation. Before that, just let's see two more finding algorithm in the binary search tree. Okay, so let's say we have a binary search tree and we want to find the minimum value from the binary search tree. Okay, so let's say the tree looks like, let's use the same example. Okay, so let's see we have the tree looks like this. So here we can have, let's see, 18 and 25. Okay, so 22, 20, say 30. And here let's add something more. So let's see 3, 6, 2, and okay, let's make it 1, and here make it 2. Okay, all right. So that's a binary search tree, and let's say we want to find the minimum value from the binary search tree. Okay, so here the set of number, here we have the set of numbers and what is the minimum value and how do we find the minimum value from a binary search tree. Okay, so before that, just find out, just think about like you have a list of numbers. Okay, the same list of numbers here, if we write it like that, say 10, 5, 20, just in the random order. Okay, 3, 6, and like all these numbers, how do you actually find a minimum numbers from a set of numbers? Okay, so that actually needs the traversing the whole items, whole list. Okay, then we're going to find which number, which value has the, which number has the minimum value. Okay, so that's the order of n operation. N is the size of the list. All right, but here what we can do, actually we know that the minimum value, where we can find the minimum value. Okay, so here the operation is actually simple because the minimum value is going to be actually the leftmost node. Okay, the leftmost node will have the minimum value. Okay, so we start from the root. Okay, so this is not the minimum value if the root has some children, obviously. So if the root has some children, if the root doesn't have any children, we can say that that's the minimum value. But if the root has at least one children, we can say that the value is less than this value. Okay, so if it has a children 5, obviously 5 is less than 10. All right, now go to 5, and if 5 has children 3, let me say that again, if the root has a left children. All right, so if the root has a left children, obviously the left children is less than 10. All right, so again go to this left of this root. So if this node has a left children, means, all right, so this value has to be less than 5. Okay, So if this value has a left children, 3 has a left children, means this value is obviously less than 3. So that's how we can actually keep going left until we find a null value. Okay, when we find a node that doesn't have a left children anymore, we can say that this is the item with the minimum value. All right, because the idea is simple. If you have a node, okay, and it has a left children with any value, all right, you can say that this is not actually the minimum value. Obviously the left children has the value which is less than x. Okay, so this is the idea, and we can using this idea we can keep going to the left, okay, until when the node doesn't have any left children anymore. So the leftmost node of a tree will always contain the minimum value. Okay, so you can actually do the experiment by writing a different tree like this. Okay, here you can see, start from here. Okay, it has a left children, so go to left. 2 has a left children, go to left, and 1 doesn't have a left children anymore, so 1 is the node that has the minimum value. Same as here. Okay, same as here, this is the leftmost node, so it is the node with the minimum value. Okay, all right. So the iterative approach to find the node with the minimum value, how can we find that? What actually we are going to do, we are going to start from the root. Okay, but here actually we are going to from each node we will only traverse in the left direction. Okay, so until we find that current is not null and current has a left children, current has at least a left children, we are going to move current to the left of current. Okay, all right. So when we find that current has a left children which is null value, for example like this one, okay, so then we are going to exit from this loop and we'll find our current value, okay, where current doesn't have any left children anymore. Okay, now using the same approach, how we can find the maximum value of a tree. Okay, how do we find the maximum value of a tree? Let's just using the same example, say just a smaller tree, so let's say 10, 5, 20. So we have like say 3 and 6. Okay, so we have here 18, 25, and let's see, we have here 35. Okay, how do we find the maximum value? All right, so the same idea, if you have a node and the node has a left children, okay, so we can tell that the node that we are right now seeing, the node x, okay, obviously the node is not the maximum if it has a, I'm sorry, if the node has a right children. Okay, if the node x has a right children, we can say that the node with the value x is not the maximum one because it has a right children x1, obviously x1 is greater than x. Okay, so the same approach we are going to implement here, but we are going to traverse in the right direction. Okay, so that means the rightmost node has the maximum value. So start from here, 10, 10 has a right children. Okay, so go to 20. So 20 has a right children. So move forward to right direction, 25. 25 still has right children, 35. Now 35 doesn't have any right children anymore. That means this is the node that we are looking for. Okay, so look at the all tree again anymore. So you can see that the rightmost node here is 30 and 30 is the node here with the highest value. Okay, again here the rightmost node is 35, okay, which is the node with the highest value. So again you can see here Okay, we should look at the here actually. So if we saw that if we want to make it a binary search tree, we have to move 7 here. Okay, so you can see that the rightmost node here is 8 with highest value, and here also. All right. So the algorithm is actually like the idea is same. All we have to do, we have to actually move to the right direction. Okay, so while we find a until we find a node that doesn't have any right children, we are going to move forward in the right direction. Okay, so when we find a node, all right, that has a right children which is null, means we are going to exit from this loop and we are going to return the node. Okay. All right, so these three are the actually finding operation. The first one was actually, so the first one was finding a node from finding any node from the binary search tree. The second one is finding the minimum value from the binary search tree, and we saw finding the maximum value from binary search tree. Okay, so in the next segment, we are going to continue with the more operations and the runtime of the operations. Okay.